Okay. Let's see. Now, okay, let's do one more example here. So example 6. Example 6. All right. So we will let's see. Yeah, that's fine. So we will let G be a mapping from R2 to R2. So this time R2 to R2 will take points in 2 space and we'll map them to points in 2 space, defined by G of R theta, I'm just going to use R theta, is equal to R cosine theta, R sine theta. So it's a function of 2 variables and you're spitting out 2 things. So this is our x and this is our y, if you will. First coordinate function, second coordinate function. Okay, and let f be a mapping from R2 to R1, defined by f of xy is equal to x squared plus 4xy. Okay, so let's see what we've got here. Let's draw a little picture. That's R2, that's R2, and this is R1. So G maps from R2 to points in R2. That's G. F takes these points in R2 and it actually maps them to R1. Therefore, we can form the composite, which is f of G, which takes points in R2 and maps them to R1. That's all that's happening here. Okay, in other words, f of G is actually going to take R theta and it's going to map them to some number, some function. So f of G is a function of R theta. G is a function of R theta. F is a function of xy. Xy are just variables. The composite function, which is a mapping from R2 to R1, is a function of the 2 variables R theta. That's it. That's all that's happening here. Okay, let's just run through the mathematics here. So, so basically what we're going to have at the end, notice, R2 to R2, R2 to R1. So f of G is a mapping from R2 to R1. So let's write that down. F of G is a mapping from R2 to R1. So what we're going to end up having is a 1 by 2 matrix. And so we're going to have df of G dr. It's going to be one partial derivative that we have, and the other is going to be df of G d theta. That's what we're going to end up with at the end. So let's just do it according to our method. Okay. Well, when we take the derivative of f, it's going to equal, well, f was a function, so it's going to be a 1 by 2 matrix, and that row is going to be the gradient of the coordinate function. So we get 2x plus 4y. You know what? Let me go ahead and write the functions again. I want you to see them on the same page as I actually take the derivatives of. So f was f of xy is equal to x squared plus 4xy. And g of r theta is equal to r cosine theta, r sine theta. We're forming f of g. That's what we're doing. Okay, so let's go ahead and take the derivative of f. The derivative of f is going to equal the 1 by 2 matrix, and it's going to be the gradient of this coordinate function. So what we're going to get is 2x plus 4y is our first. I'll leave it as a matrix so I won't have columns. I won't have commas. And then the derivative with respect to y is going to be 4x. That's our derivative of f. Okay, so now we're going to take our derivative of f and we're going to evaluate it at g. G is this, okay? That means take this and take this as our x and y and put them into here because we're forming the composite function. So we end up with the following. We end up with 2r cosine theta plus 4r 2r sine theta, and we end up with 4x, which is 4r cosine theta. So this is our first. Now we'll do dg. dg. Well, dg is a mapping from R2 to R2, so it's going to be a 2 by 2 matrix. So the first row is going to be the gradient of that function. The second row is going to be the gradient of that function. So it's going to be, the derivative with respect to r is going to be cosine of theta, and the derivative with respect to theta is going to be minus r sine theta. Now this function, the derivative with respect to r is going to be sine theta, and the derivative with respect to theta is going to be r cosine theta. There you go. And now we'll go ahead and actually do the multiplication. So the derivative of f of g, the composite function, is just equal to, let me put, is equal to this thing times this thing in that order. This one goes first. So we'll write 2r cosine theta plus 4r sine theta, and then we'll have 4r cosine theta. So this is our matrix there. And then we're going to have cosine theta minus r sine theta, and then we have sine theta, and then we have r cosine theta. Oops, there we go. This is a 1 by 2 matrix. This is a 2 by 2 matrix. The middle things go away. Our answer is going to be a 1 by 2 matrix. So we're going to multiply this by that. That's going to be our first entry. And then we're going to multiply this by that. That's going to be our second entry. And again, I'm presuming here that you've seen matrix multiplication at the very least. I know that you have in high school, and I know that you probably did a little bit of it in calculus, at least here or there. So I know it's something that you're familiar with. And again, if not, no worries. This section is not going to show up anywhere else. So you're more than welcome to ignore it if you want to. Okay, so now let's do this multiplication. When we actually multiply it out, here is what we get. We get the derivative of f of g is equal to 2r cosine squared theta. I'm going to write it vertically, plus 4r sine theta cosine theta plus 4r sine theta cosine theta. Now I can put some things together. That's not a problem. 4r sine theta cosine theta, 4r sine theta is 8r sine theta cosine theta, but I'll just go ahead and leave it like this. So now our second entry is going to be minus 2r squared sine theta cosine theta minus 4r squared sine squared theta plus 4r squared cosine squared theta. Okay, this is what we've ended up with. Our composite function f of g, the derivative of that is this right here, this whole thing. Okay, now f of g was a mapping. We said that f of g was a mapping from R2 to R. We know that its derivative is going to be a 1 by 2 matrix. This is what we've got. We've got a 1 by 2 matrix. 1 row, 2 columns. Okay. This right here, f of g, was a mapping, was a function of r theta, right? That was the original departure space that left. So it is a function of r theta. Therefore, what we have when we take this derivative is d of f of g dr, d of f of g d theta. That's that one. That's that one. That's all that we have done here. Okay. I hope this helped a little bit. You know, if not, don't worry about it. It's just something that I wanted you to see, a little bit more of a global idea, something that generalizes to mappings from a space of any number of dimensions to any number of dimensions to demonstrate that we can still do calculus. And this is actually kind of extraordinary that we are not limited to a single space. We can work from two entirely completely different spaces, mapping from one thing to the other, and we can still do calculus on this. The ideas are the same. We're just taking derivatives. Now, instead of a derivative being a single function, now a derivative is a matrix, and the matrix can be of any dimension. And in those matrix, the entries of the matrix are the actual functions that we deal with, the partial derivatives, if you will. So thank you for joining us here at Educator.com, and next time we'll go ahead and continue on with our discussion of maxima minima. Bye-bye.